Hello everyone. So today we'll be discussing about arithmetic logical operations that have been discussed in the previous session. So let us continue further with few examples over here. So the next I'm going to speak about array description language and their importance. Then you will be describing Verilog HDL. Then describe what is the structural, behavioral and data modeling styles in Verilog HDL. So you will be able to write Verilog code using 3 models to design digital circuits. So end of the session you will be aware of all these concepts. So as I discussed in the previous class about arithmetic logic unit, once again I need to refresh the functionality of arithmetic logic unit. So it is a multifunctional device that can perform arithmetic as well as logical functions. So it is an integral part of CPU. As you know, CPU performs arithmetic and logical operations. It can also perform increment, decrement operations, and there will be a mode selector which decides what kind of operation I want to perform. It could be an arithmetic operation or it could be an logical operations. So in each mode different functions are chosen by activating selection inputs. Let us see those. IC of 74181, that is of ALU. So look at this IC. This is 74181 IC, which is a 4-bit ALU. So we have taken an example of 4-bit ALU here. You can see this IC which is of 24 pins. So we have 4 selection inputs, S3 to S0, and we have A3 to A0 inputs, a set of inputs, B3 to B0 sets of another sets of input, and we have output which is we call it as F3 to F0. We have a mode selection M. You can just see over here M. So M could be can be made 0 or 1 based on what kind of operations you want to perform. It could be an arithmetic operation or it could be an logical operation. So you can see here S3, S2, S1, S0 selection inputs, and we have F0, F1, F2 and F3 as an output, and we have A1 to A2, A3, A0, B1, B2, B3, B0 as an inputs, and M acts as a mode control here to select between arithmetic as well as logical operation. And we have another set of outputs, that is Cn, G and P, where these bits are particularly used whenever you do operations like addition and subtraction. If at all you are performing more than 4 bits. So we have here G, P, Cn and Cn plus 1. We can call this as Cin and as well as C0. So you can just see this functionality. So we have this IC 74181 set of selection inputs, set of inputs as I discussed, and mode control, and we have outputs over here F3 to F0, and we have additional outputs to give the status of addition or subtraction operation. Since I have 4 selection inputs, I can generate over here 16 combinations of the functions that can be performed here. Either it could be a logic or arithmetic function as I discussed, right. So if I make mode as 1, then I am going to perform logical operation. So here are the sets of functions which can be performed, logical functions which can be performed based on whatever the input selection lines I am giving. Similarly, when mode is equal to 0, I will be performing arithmetic functions. So provided I should make Cin as 1 whenever I perform arithmetic function, else I should make Cin as 0. So I will take up an example over here. Suppose you want to perform logical operation, that is not complement operation, then I need to give the inputs for selections as I can see in this table 0, 0, 0, right. My output will be the complement of A. So, whatever the inputs you are giving, for example, I am giving 1, 1, 1, 1 over here. So, when I apply this selection lines, so my output over here will be 0, 0, 0. So, similarly, I can perform all these operations as you can see here. I can perform complement, 1's complement, 2's complement, addition, subtraction, division, multiplication. Directly I can't do multiplication. As you know, multiplication is the concept of shift operation. We will be using shift performance for getting the multiplication operand. Let us take some example over here. So, example here, show how bits of A to be shifted left by 1 unit and appear at the output F in IC 74181. So, what are the inputs I am going to take now? So, the inputs are A. So, I have taken an example A, the inputs as 0, 1, 1, 0. Okay. Since I am performing arithmetic operation here, so I am making mode selection 0. Shifting to left by 1 unit is equivalent to multiplication by 2, as you know, if you want to do any multiplication operation. So, now I am making Cin as 1. Since I am performing arithmetic operations, I need to make Cin 1, right. So, my selection lines 1, 0, 0. What is this 1, 0, 0? So, according to the previous table, 1, 0, 0. You can just see here. So, 1, 1, 0, 0. If you go to the previous table, 1, 1, 0, 0, under arithmetic function, you will have output as A plus A. It is nothing but it gives the operation A plus A, your output should appear. So, what exactly I am doing? I am doing shift operations here. If my input is 0, 1, 1, 0, so it will be shifted left here. So, the bits will be shifted after giving this. So, this is one example. Second example, how can I show that A is greater than B? So, as usual, I will be giving two sets of inputs over here, 1001 and 0101 for the inputs of IC 74181, and I make Cin 0 since it is arithmetic operation, and I will be using select input 0110. So, this is nothing but to check A greater than B, I will be subtracting. So, to use this A minus B function, I will be using the selection line 0110. So, but for Cin is equal to 0, the output appears as A minus B minus 1. I need to check out the carry once again to check whether A greater than B. So, these are the set of inputs I will be using this in IC 74181. So, now let us discuss a concept called hardware description language, which is basically used in digital circuit design. So, what exactly is this hardware description language? So, under hardware description language, we have two sets of language, that is VHDL and Verilog. So, in this description language, I will be discussing about Verilog. So, what is a Verilog? Verilog is hardware description language used by hardware designers in industry, as well the academicians can check to do for research purpose, they can check their design using this language. So, whenever the digital system is more complex, I am going to design, instead of designing on board, I can design on the tool and I can verify whether my circuit or my system is working properly. So, Verilog language provides the digital designer a software platform where I can check my functionality. So, what exactly it does? So, it allows users to express their design with different constructs, we can call it as behavioral constructs. So, program tool can convert this Verilog to program to a description that is used to design chip. a tool that can convert this program to describe the design chip. There are various tools available to design this Verilog coding, design and verify this Verilog coding. So, let us discuss how this language constructs and how we describe this language. So, you can just see it has got many keywords. I have taken some few examples over here. I have listed few. First one is module, which is used to define the starting. This is the starting keyword to define your entire what module you are going to define. So, what is the design you are going to define? You will define it by a name. The name is called as module name, and you are definitely you are going to end this module by giving the keyword end module. So, end module is ended with this definition. Then we have an keyword called begin, which is used to begin in front before I start a set of statements. So, before I start a sequential statements, I should declare begin. So, begin is nothing but a set of statements in a block start with this keyword. End, once I complete the set of block of statements, then I need to end this block by giving the keyword end. If statements are used to verify certain conditional statements. Likewise, we have many keywords available in this Verilog module. So, let us discuss how the program structure looks. So, first the program begins with the keyword as I described earlier. Module is a keyword. So, it is enclosed with the bracket which gives the port list. So, what is this port list? It is nothing but a list of what are the inputs, outputs and in-outs. In-out is nothing but an intermediate variable that is acting as both input as well output. So, that are listed in this. These are the parameters that are listed in this port list. After this module, now I am going to declare what functionality I should perform. So, declaration is nothing but it specifies the data objects. It can be in registers, memory, wires or any other procedures or functions and tasks what I am going to perform, that will be declared over here. And then I will be declaring the end module name. Module with the module name, it is an identifier which is a unique name representing this module. The functionality is declared in the declaration function, and then we will be ending this module by the keyword end module. So, this is a program structure used to design Verilog code. There are 3 modeling styles in Verilog. So, let us discuss each style. So, how it is different from each and how you can design the logic design circuits using this coding. So, we have a structural modeling. It is also called as gate level modeling. I am going to define the design with respect to gates. So, there will be an predefined gates, primitive gates defined. So, we can use those gates to describe my circuit. In the data flow modeling, I will be using assignment statements, keyword assign. In a behavioral modeling, I will be using procedural assignment statements by giving condition called always. So, these are the different styles. Let us take an example for each style of modeling to define a particular circuit. So, let us define the structural model of NAND gate. I have taken a simple example of NAND gate. So, as you can see, the NAND gate has 2 inputs and 1 output. So, I am going to describe now the Verilog module based on the structure, how the gate looks, what should be that inputs and what should be my output. So, there will be a predefined gates inside this Verilog code. So, you can just see this module. I have given the module name as my underscore NAND. So, you should not give directly as NAND since it is a keyword. So, the module name should not be a keyword. Take care in such a way that the module name and the keyword should not be same. And I will giving you, this is the port list. So port list is nothing but the set of inputs and outputs. You can just see here A, B and Y are the three variables I have declared. So now I am going to define which are the inputs over here and which is the output over here. So by giving a keyword input A comma B semicolon. So each line has to be terminated by semicolon and it is case sensitive. So if you are using capital A, the same thing has to be declared here. So output Y. Now the functionality begins here. So the function over here is, I am using the keyword once again here, NAND. NAND is a keyword with the name of this gate. I have taken the name of this gate as G, which has got always the functionality start from output and then input. Your first parameter should be an output followed by the inputs. So immediately a NAND gate will be designed if you give this functionality. This structural model can be written only if you are aware of the circuit. So you are aware of the circuit, you are going to define the variables and then you are going to write a model, structural model for the particular circuit. So I will take up one more example for this. Let us take up a simple circuit. Say I have two gates with two variables each and there is an OR gate at the output side. So I will treat this as G1, G2, G3. So how do I write a structural design, structural model for this particular logic circuit? So as I said, I am going to start with the module. I am going to write the circuit name, module name as logic underscore circuit. Now I am going to list the possible inputs. Available inputs over here are A, B, C, D and I have got only one output. So this is the declaration, data declaration. Now I am going to define which are the inputs and thus. So I am defining inputs in this, no bracket here, you have to write the brackets only in module name. So now input, two inputs we have A and B, comma, C and D, semicolon, and A, B, C, D, 4 inputs, one output Y. Then I am going to define now how many gates we have here. We have here 3 gates. So now we are going to define the first gate as G1. So the first gate is AND gate. I am going to define keyword AND with the AND gate name as G1 and the output of this, say it is Y0 and this is Y1. So this will be your temporary variable. So to define this gates, so I am going to now write this output comma A comma B. Always the first parameter should be your output followed by inputs. So this is with respect to gate 1. Now the first gate is created. Once I declare this model, this line, you will be creating one gate, that is first gate with 2 inputs and 1 output. The second gate, once again I declare the output is Y1 in this case, inputs are C, D, semicolon. Now I have designed second one. So once after these 2 lines, 2 gates are already ready. So the third gate is G3, so which is OR gate. So my output is Y, my inputs are now it is Y0, Y1. So finally I am going to end this module by writing the keyword end module. So this AND, OR are all predefined gates. So as I give this keyword, automatically the gates are generated. Similarly, we have many gates, universal gates, basic gates, which are all predefined. This is how I am going to write the structural module of any circuits. It can be any circuit. Whatever may be the number of gates, I can generate that particular logic circuit by defining each gate with inputs as well output. So let us discuss next example. Full adder. So take an example of full adder. In the previous class we have discussed how to design a full adder. Full adder has got 3 inputs, 2 outputs, sum and carry. So finally I get an expression for full adder for sum and carry. You can just see for sum I have A XOR B XOR C. For carry I have AB plus C and then A XOR B XOR C, then you will get C out. So this is your circuit diagram of full adder. So you know the circuit diagram of full adder. Now I am going to write a module, Verilog module for this full adder. So as I said, module, the module name is full adder. So what I am going to write now, the sets of inputs and outputs. I have declared the input A, B and C in, output S and carry out. So now I am going to use here wire. So why wire here? So wire is nothing but a connection, intermediate connections. So that is what I am going to explain now in this. So in the previous example also, what I should do with this, it will never identify Y0, Y1 until unless I write wire over here. So what is this wire? This is nothing but an intermediate connections which is not visible, which is not declared in the module port list. So this wire what I can give as Y0, Y1. If I am not using this line, definitely these 2 lines are not recognized. So you need to declare the wire which is an intermediate connections, so which is not declared in the port list. So that is nothing but a wire is a keyword for connections. So let us discuss. For full adder, I am using wire here, S1, C1, C2, C3. C3 is been not used here. So first XOR gate, as I said, XOR is a keyword. So I will be declaring now the functionality. First is output, the port list, and the inputs are, now this will be S1 and the inputs are A and B. For second XOR gate, it is output is S, the input is C in, and output of this, that is nothing but it will become input. This is S1, and the second AND gate, now here it is C1, C2, C3 is not there. So we have only C1 and C2. AND gate C1, output of AND gate I will take the variable as C1, and input of AND gate is, you can just see here, this is C in and C in and A B, you can just see here A B C1, second one is C2, then S1 and C in. So this is how I am going to generate for 2 XOR gates, 2 AND gates and 1 OR gate. So OR gate is C out and these are intermediate variable C1, C2 here. So the intermediate variable over here is S1. So finally I will be generating this circuit full adder using structural model. So let us discuss data flow model. Take an example of 4-bit adder. As we know, 4-bit adder, I will be using 4 bits of A and B, A0, A1, A2, A3, B0, B1, B2, B3. So to declare that 4 bits, I use 3:0. It is nothing but the most significant bit, A3, A2 till A0. So 3:0 represents 4 bits of A and 4 bits of B. You can just see here 3:0 A comma B. This is nothing but there are 4 bits of A and 4 bits of B, that is declared in a bracket 3:0. We have input C in, carry in, and output also. The sum will be 4 bit 3:0 and output C out. Since I know the equation, the functionality of 4 bit adder, directly I am using the statement assign. So what does this assign statement do? So assign, I am assigning the outputs C out and sum by using this variables A plus B plus C in. So it is going to add two 4 bit numbers along with the carry. So you will get the output sum as well as C out. So this is nothing but data flow. I am just concentrating on how the data is flowing rather than on the structure over here. So we are going to use an assign statement in data flow modeling. So take an example of 2:1 multiplexer. As I know, in 2:1 multiplexer, we have only one output, 2 inputs and selection lines. So you can just see here the declaration AB and selection line, one will be output. So I am going to use a assign statement over here. Assign this output variable by using with respect to the selection line. If my selection line is 0 0, then select A, else select B. So this question mark indicates if the condition, the first condition is true, then select this particular first variable, else select the second variable. So I am going to assign this output by using the statements here. Similarly, this 2:1 mux in data flow description, I can write in the other way also. So you can just see using this gates. So we have the circuits of 2:1 mux. So I can give the declaration here, A as a selection line, 2:1 output, 2 inputs D0 D1. So I am using inputs as selection as well as data inputs. My output will be Y. I assign not of A and, it is logical and operators we are using here, either this function or this function. Either I am going to choose this A complement D0 to the output side, or I will be using A D1 to the output side. So we are going to use operators here. We are going to assign operators here. This is an OR operator which will be choosing this or this based on what selection line you are using. So this is an example of 2:1 mux written in data flow modeling. Let us discuss behavior description, how to write Verilog code for half adder using behavioral description. So let us see, I am giving the module name as add off, and we have set of the port list with inputs and outputs. Here I am using, whenever I talk about behavioral modeling, I will be giving a conditional statement called always. So after the declaration of inputs, outputs, so I will be using one more term here, reg. Here it acts as a temporary variable, it's a register which stores your output temporarily. So I need to always use reg whenever I use always statement. So always at, it is a conditional statement, always is a keyword at either A or B. So the two conditions here A or B, begin. Now the begin starts with the set of statements are declared here. Before I decide or declare the set of statements over here, I should start with begin. So begin, I will give statement over here, sum. What is sum here? it's A XOR B. I have used an operator here, XOR operator. What is carry? It is A and B. So I am using operators here. I will start, since begin is followed by statements, it is sequential. So I am going to get sum, then carry out. So always the begin has to be enclosed or closed by end statement. Then comes end module. So always these two statements works based on A or B. So this is the condition given. Take up an behavioral model of 2:1 mux example. So previously also we have designed 2:1 mux using Dataflow model. Now let us discuss using behavioral model. You can just see same over here, selection line 2:1 mux, since we have 2:1 mux, 2 inputs, 1 selection line and 1 output line. The set of inputs over here and an output here. So always I use a reg, a temporary variable, to store my output. Whenever I use always statement, I need to declare this reg statement. So always at either A or D0 or D1, in the sense if any of this variable is going to change, then my functionality is based on A. I am using case statement here followed by the condition. So case statement followed by A. If my A changes, if my A is 0, then my output will be D0. If it is 1, the case statement now here either 0 or 1 for the variable A. So that's why I have given in the bracket A. So as you use in C language, switch case statement. So here 1, then Y will be D1. So I have to, since I am using case statement here, I need to end this with end case statement. So in the previous I have used begin statement, I need to end there. So similarly here I use case statement, I need to end this case statement by giving end case followed by end module. Let us discuss 4:1 multiplexer. So in this we have module 4:1 mux, name as mux4. I have got selection, I have got D and Q. D is an input, Q is an output. So since I have declared here variable, I can give how many bits over here? My selection lines will be 2. So that's why my input is 1:0. We have 2 bits selection line, we have 4 bits input, we have 1 output. I am sending this once again output. I am storing this in a temporary variable reg Q. Q is an output. So once again we are using here wire. Note that wire is nothing but an intermediate variable. I have declared here as an input. I am using once again the variables over here. Since my output is of single bit, I have used Q. My inputs are of here 4 bits and 2 bits. I am using wire. Always at select or D. Select or D, either the select or the D variable is going to change, then I am using case statement over here for select, begin followed by the set of statements here. So it will be sequential. If select is 0, then my output is nothing but D of 0. The first input is redirected to the output. So if it is 1, the second input is redirected to the output. Similarly, for all 4 inputs based on the selection lines, you will get the output. So I have to end this with end case and then it is end module. You can just see here behavioral module of ALU. So ALU, as we have discussed the operations of ALU. So it is a multifunctional circuit where I can perform arithmetic and logical operation. You can just see here I am declared here module. You can see the module name as ALU. I am using variables AB, opcode, OOP, operation. So, my output will be multiple outputs. So, I have taken 8-bit here to define my outputs, and I have taken my inputs to ALU also 8 bits. So, if I am taking my inputs 8 bits, right. So, I am declaring 7:0 and I am using control. As you know, S3, S2, S1, S0 are the control lines for ALU. So, I have input 3:0 with the variable opcode. This is for control signal for different operation. Note that you can write the commands by giving slash here. 2/ will represent, this is a comment line. So, it always the line is ending with semicolon. Now, I am using always at either of this condition begin. I am using case statement with opcode. So, this is what if this opcode is going to change, based on this my output will be redirected. So, 4 represents, it is a 4 variable. I am using 4 variable here. So, in the selection lines are 4 variable, 4 selection lines we have. So, 4 tick B, B represents binary. If I am representing the number in binary, I am going to write B. This is the syntax used. If I am using an octal, it will be O. If it is an hexadecimal, it will be H. So, I am going to represent 4 tick B00, then colon, begin opcode is equal to A plus B. It is going to add 2 numbers. So, I am going to use 2 sets of numbers here, A and B. Similarly, I can perform subtraction operation, multiplication operation, division, then modulus, and operation or operator, logical and, then as well shift right, shift left operations. You can just see over here, I can perform increment, decrement, whichever the operations you need to perform, I can give based on the selection lines. I can declare here, and then I can give one more condition as default code as XXX, it is nothing but non-determinant. So, I will be closing this case statements using end case, and be closing this begin statement with end. I will be closing this module with end module. So, this is the behavioral model of ALU. So, we have discussed today about arithmetic and logical operations using ALU, the importance of hardware description language, and how to write Verilog code using 3 models to design digital circuits. So, by using the Verilog style or VHDL style, I can design complex circuits using this programming construct. I can verify these circuits using test bench waveform for all different combinations of inputs to check my functionality. It is easier rather than directly giving it to the manufacturer. So, the design can be verified and tested in this tool, and then can be directly given for the manufacturing. So, this reduces cost as well as time for the manufacturer. So, designing any logic circuits, whether it is complex or simple, which makes easier by using tool. This tool can be used by operating these 2 languages, hardware description language. I am describing the hardware in terms of language. So, that is nothing but hardware description language. Thank you.